Good morning, everyone. Welcome to the most comprehensive preparation app for all exams, BYJU'S Exam Prep. And warm welcome to the session. Dear friends, the Maha Marathon for computer organization and architecture, based on students' request, based on your demand, I have come up with this COA Maha Marathon exclusively for ECE students, right? So in this session we will be covering all the COA part in one shot. In one session, complete COA will be revised for you with questions. Okay, so guys, please join the session quickly and mark your presence. Also, could you please confirm my visibility and audibility? Am I visible and audible to you clearly? Everyone who have joined the session, please confirm, am I visible and audible clearly? Harshal, yes, okay. Everyone please do confirm my visibility and audibility. Okay. All right. So, computer organization exclusively for ECE students, we will have the Maha Marathon today. Before that, let me introduce myself quickly. I am Satya. I am a research scholar. I have 15 plus years of teaching experience. I have mentored more than 35,000 students in the GATE and PSU segments. I am qualified in GATE, UGC NET, SET and certified by Cisco. And these are my areas of expertise in computer science, PDS, programming data structures, algorithms, computer networks, computer organization and architecture, operating systems. Harshal Purohit, we will have the questions related to only our syllabus, whereas the CS COA has so many concepts, right? So you don't have all those concepts in your syllabus. So this is exclusively for you. Questions, yes, some questions would be same because the topics are same, and some standard questions will be there, same questions will be there. Okay, it is for EC, it is exclusively for ECE students. Dreamer, Himanshu, good morning. Maunika, okay, chalo. So guys, we have come up with this master MSQ series for you for electrical, electronics, instrumentation and computer science students. By attending these series, these classes, you can definitely be a master. You will know how you have to approach for these MSQ model questions through this from 17th January, that is today, this series is getting started. So attend regularly. Okay, our favorite Asutosh Saxena sir will be taking a session. This is very important for you guys, ECE students. How to become an IES officer in the first attempt. In the very first attempt, how you can become an IES officer. What are the tips, tricks and what should be the strategy that would be shared by our favorite Asutosh Saxena sir today at 7:30 p.m. So try attending this session, it would be very useful. All right. So guys, for ECE, for electronics and communication engineering students, in the GATE, recently this computer organization is included, as we all know. From this syllabus, we will be getting the questions. What is the syllabus? What are the topics we have? We just have 4 topics, and if I divide them all together, they become just 6 topics. Machine instructions, instruction formats, addressing modes, ALU data path, control unit design, instruction pipelining. So these are the topics we have. Other than this, you need not to prepare any one single topic also from this computer organization, right? And what would be the weightage? Definitely this is the one question you will get. Sir, how many marks we can expect from this CO related concepts? I will be telling that weightage. The expected weightage is 4 to 6 marks. Like we can expect 3 questions minimum, like 2 1-mark questions, 1 2-mark question, like that. Minimum 4 marks we can expect, and it may extend to 4 questions, maybe 5 questions, but 3 questions minimum you will get for 4 marks, and it can vary to 6 marks also. Okay, I think the syllabus and the expected weightage is clear for everyone. Please confirm so that we will start. Everybody. Okay. So let us start first with the topic machine instructions. Okay, as you people are looking for one single class where you can revise all the CO, first quickly I will give the brief of the topic, then we solve the questions. Okay, firstly, whenever you say instruction, what is instruction? Instruction means it is any executable statement, means to perform a task, to perform certain activity or certain job or operation. If we write any statement, provided that is the computer understandable language, means in machine language or in the assembly language, if you write some statement, that statement is what we call as instruction. And the format, generally how the instruction looks like or what would be in the instruction means, there will be mode field, this is what addressing mode, followed by opcode that specify what operation to be done for the ALU, operands information, means using what the instruction should be, operation should be performed. For example, add R1, R2, R3. If you take this, here mode I have not included, because once we see addressing mode, then we will understand. So this is the opcode that specify the operation to be done is addition. And using what? Generally, the last operands, first operand is generally considered as destination operand. The next 2 operands are considered as source operands. It is not mandatory, the format can be changed, but the default you can say destination operand followed by source operands. So it means that add R2 value and R3 value, store that result in register R1. So if we want ALU to do this operation, In this way, we write the statement. This is what we say instruction. Okay. Now, these instructions can be classified basically into three types. How? Based on what operation ALU is doing. What kind of operation ALU perform. Based on that, instructions can be classified into three types. What are they? Data manipulation instructions. Means which modify. Manipulation means what? Modify. Which modify the data. Data transfer instructions. The name itself suggests that transfer data from one to other, like from memory to CPU, CPU to memory, input device to CPU, input device to memory. In this way, here or there, the instruction that make data to copy from one to another, that is data transfer instruction, and program control instructions. So, data manipulation instructions modify given data. Data transfer instructions copy the data. Program control instructions, what they do? They change sequence of execution. In what order these instructions should be executed, that order can be defined, modified by program control instructions. Okay. Now, data manipulation, if you look at what that mean, because of that instruction, ALU modify the data. Means by doing what operation ALU data will be modified? By doing arithmetic operations, by doing logical operations, by doing bitwise operations, by doing shift operations. Means if you add, value will be modified. Subtraction modifies. Multiplication, increment, shift, and or. By doing any of these operations, data gets modified, no? So, these data manipulation instructions include these operations. Means these related opcodes in the opcode field. In this field, if you find any operation related to arithmetic, logical, bitwise, shift, that is data manipulation instruction. So briefly, here I have presented what different arithmetic, logical, bitwise, shift opcodes you will have. You can see here, increment, INC, decrement, DEC. Actually, increment means, INC means increment with carry. It's not just increment, increment with carry. Similarly, decrement with borrow, addition, subtraction, multiplication, division, add with carry, subtract with borrow, negation means complement. 2's complement, dear friends. Okay. Similarly, you can see logical and bitwise, that will have the opcode as clear carry. Complement, complement means here 1's complement. Logical and, logical or, XOR, clear carry. Here just CLR means clear accumulator you can take. CLRC means clear carry, clear the carry flag. Similarly, set carry to 1. Complement carry, enable interrupt, disable interrupt. And shift operations, you see shift right, shift left, arithmetic shift right, arithmetic shift left, rotate right, rotate left, rotate right through carry, rotate left through carry. Here I would like to mention one point, dear friends. Shift left. Suppose you want to shift some A value left, let's say by n times. That is equivalent to A multiplied by 2 power n. Similarly, you would like to shift right some A value by n times, that is equivalent to division by 2 power n. Remember this would help you in the questions or somewhere. Clear? These are different data manipulation instructions. Then data transfer and program control instructions you see here. Load, store, move, exchange, in, out, push, pop. Sir, what is the difference? Load means from memory to CPU data gets transferred. Store, CPU to memory. We have some other synonym instructions. Load is equivalent to read. Store is equivalent to write. Okay? And move between among the CPU registers or within the memory if the data need to be transferred, move. Exchange for interchanging of the values. Input from input device to CPU or memory. Out from CPU to output device or memory to output device. Push. This is the input to general purpose registers, GPR stack. All the general purpose registers are grouped together and used in the LIFO order. What order? LIFO, last in, first out order. In this order, when the operations are getting happened, we say that data structure as LIFO, last in first out data structure, that is stack. So for stack, input operation is called push operation, and from stack to output, so data is getting transferred from the GPR to output device or memory, that is pop. Okay. Similarly, here you see program control instructions. Being ECE students, you are well aware of this. In the microprocessors, you will get all these. Branch, jump, skip, call, return, compare, test. And dear friends, what is BUN? What this opcode means? Could you please tell me? What does this BUN is? Kaushalya, Harshal, Himanshu, Dreamer. What does this is? Yep. Branch unconditionally. And what is BNZ? What does this BNZ represents? Branch. BNZ means what? Branch if not 0. What not 0? Accumulator value not 0. Right? So because of these instructions, the control gets transferred, means the order of execution gets changed. Remember these instructions, everybody. And whenever we say instruction, when any instruction is getting executed, generally they include 3 phases mandatorily. Exactly, Monica. Branch if not 0. When any instruction has to be executed, there includes 3 steps. Fetch, decode, execute. These are the mandatory phases for any instruction, whether it is arithmetic, logical, data transfer, data program control, whatever the instruction it is. For any instruction, these 3 stages will be there mandatorily. Fetch. What does this instruction fetch? Here, fetch means 2 types you can say. Instruction fetch operand fetch. Instruction fetch, operand fetch. What is this instruction fetch, operand fetch difference? Instruction fetch means the required instruction is in the memory. That instruction copying from memory to instruction register. This is what we say instruction fetch. So fetching means basically loading from memory to CPU. So what we are fetching? Instruction. Hence it is instruction fetch. Operand fetch. What is operand fetch means? As an instruction fetch is loading instruction from memory to CPU. Operand fetch is loading operands from memory to CPU. CPU means what, sir? Memory data register or temporary register or accumulator. The obtained data can be in the DR, TR or AC, but directly it won't go to temporary register or accumulator. Directly where it goes? To the data register only always. This is what we say operand fetch. Right? And decode. Decode is what? Analyzing the copied instruction. That means sequence the operations. In what order this instruction should be performed. That sequencing is called decoding. Which unit perform decoding? Decoding is solely control unit job. What unit will perform? Control unit will perform decoding. Okay? And then execute. Execute means what? Doing that operation. Performing the operation specified in the opcode. This is what done by ALU. ALU is the unit which perform any operation and all the operations in the computer. But ALU cannot do on its own. For ALU, what is needed? Control unit command is needed. So, we can say control unit will pass operation or command or instruction to the ALU. Then ALU perform operation. Right? Now, whenever we have series of instructions, let us suppose there is a program. This program has, let us suppose, series of instructions like I1, I2, I3, I4, I5. let's say 5 instructions are there. Let I1 is something like load R1 comma 3000. I2 is something like load R2 comma 5000. I3 is add R1 comma R2. I4 is somewhere like store 4000 comma R1, and I5 is something like halt. Suppose this instruction size is, let us say, 2 words. Second instruction size is 4 words. Third instruction size is 8 words. Fourth instruction size is 1 word, or let's say 2 words. Fifth instruction size is 1 word. Sir, word, what does that word, sir? Word means when you take a 16-bit processor, word size is, word length is 16 bits. When you take 32-bit processor, word length is 32 bits. When you take 64-bit processor, latest processors, 64 bits. So that word length is what? Design dependent. Based on the processor configuration, that word means how much varies. Okay? And why the instruction size you are writing in words, sir? Because from memory to CPU, suppose this is memory, this is the CPU. From memory to CPU, the communication takes place with only 2 registers, dear friends. What are they? Address register, data register, or buffer register. These 2 registers only communicate with memory. That's why we have n number of registers in the CPU, but only these 2 registers are having the prefix memory. Memory address register, memory data register, or memory buffer register we say. No other register has this memory prefix. Think once. We don't say memory program counter. We don't say memory accumulator, memory index register, memory base register. We never say that. Only for these 2 registers. Only these 2 registers are in communication with memory. Right? So anything you give to memory, you take from memory, that will be through these 2 registers. Now, this register capacity, MAR or MDR capacity is what? 1 word. So at a time, how much you can take or give to and from memory? 1 word at a time. That's why memory organizes its data word wise. Hence, I can say by default, memory is word addressable. Word addressable means what? 1 word, 1 address. Okay. Now, if the memory is byte addressable for a while, let us consider the memory is byte addressable. Means at a time you can copy 1 word only. 1 word only. 1 word means here what you can understand? 1 byte? Not needed. See, 1 word is 4 bytes. Every byte has the address. So do you give 4 addresses? Not needed. Starting address if you give, that is enough. All the word can be copied. So please understand, memory may be word addressable or byte addressable. But by defaults are what? Word addressable. So that the communication between CPU and memory will be very efficient. If the memory is byte addressable, whereas CPU fetch or store word at a time, then that becomes little messy communication. Means for us, not for the MMU, not for the controller, for us. Yes, Maunika. At a time, how much can be fetched from memory? How much can be stored into memory? That is what one word we say. Okay. So, let this program, when stored in the memory, let the starting address is, let the starting address is, let us say 1000. In decimal I am writing for comfortability. I know, you know, addresses will be represented in hexadecimal notation, but for comfort I am writing in the decimal. Okay. So if this starting address is 1000, then if these instructions are stored serial manner, means line by line, how the addresses would be? The addresses would be 1000 one address, 1001 another address, because the size is 2 words, so 2 addresses. Similarly, the next address 1002 would be the starting address of I2 to 1005, 1006 to 1013, 6, 7, 8, 9, 10, 11, 12, 13, 8 addresses, because the size is 8 words. In that way, 1014, 1015, 1016, only one address. Like this the addresses would be. Right? Now, if I write the size in bytes, let one word is equal to 4 bytes, I say. And if the memory is byte addressable, 4 words mean 2 words means how many bytes? Size in bytes 8 bytes, because one word 4 bytes, 2 words 8 bytes, 4 words 16 bytes, 8 words 32 bytes, 2 words 8 bytes, 1 word 4 bytes. If given the memory is byte addressable, then what would be the addresses? Byte addresses would be what? Starting from 1000. Now 8 bytes, 8 addresses. So 1002, 1007. 1008 to 16 bytes. 1023. 1024 to 1055. 1056 to 63. 64 to 67. Like this, the byte addresses are given. Okay. Now, while executing certain instruction, if interrupt occurred, are everyone clear how this instructions addresses I have written? AVSR, yes, definitely sufficient. That's why I am revising it. And this is not only theory session. Theory is less. Brief I am giving. I am giving the brief. After this, we will solve questions based on this instructions. Okay. Now, when an interrupt occurs. What is interrupt? Being ECE students, I need not to introduce this. Interrupt, a special instruction that seeks CPU service. These interrupts, we know basically two types. What? Maskable interrupts, non-maskable interrupts. Means the interrupt whose service can be delayed, that is maskable. Which can't be delayed, it should be immediately serviced, then non-maskable. AVS are definitely sufficient beta, definitely sufficient. Okay. When an interrupt occurs, the external interrupts are taken as, means IO interrupts through input or output device. Whatever, while printing you are using keyboard, mouse, while downloading you are using some input output device, while some instruction is happening, when any input or output device is used, that is taken as IO interrupts, input output interrupt, which is external interrupt because it is occurring from the external source, right? So IO interrupts are generally taken as maskable interrupts. Okay, so when an interrupt occurs during an instruction execution, while an instruction is getting executed, if an interrupt occurs, then as we treat these interrupts as maskable. Maskable means this service can be delayed, means immediately you need not to, CPU need not to address it, attend it. So what happens? While an instruction is getting executed, if interrupt occurs, then the current instruction execution is completed. The current instruction execution is completed first. Then interrupt is serviced. Then interrupt is serviced. Okay. So listen carefully. Suppose I have 5 instructions, I1, I2, I3, I4, I5. Assume instructions as I have written like add, sub, load, store kind. Let the instructions size in words is 2 words, 4 words, 8 words, 2 words, 1 word. In bytes, let's say I am taking 1 word is equal to 4 bytes. So it would be 8 bytes, 16 bytes, 32 bytes, 8 bytes, 4 bytes. Addresses, we know how we write the addresses, word addresses. Let the starting address is 1000. So 1002, 1001, 1002 to 1005, 6 to 13, 14, 15, 16. Same if I want byte addresses. Byte addresses. Then 1002, 1007, 1008 to 1023, 1024 to 55, 56 to 63, 64 to 67. Now, suppose if interrupt occurred during instruction I3. While I3 is getting executed, interrupt occurred. What did I say? That I3 is completed. Let interrupt occurred from some address 5000. at 5000 address there is some instruction IX. This IX is interrupting CPU. As it is treated as a maskable interrupt, that current instruction execution should be completed and then interrupt should be serviced. That means after I3 what should be serviced? IX should be serviced. But we know while an instruction is getting executed, always one register point to the address of next instruction. What is that register? Program counter. So program counter was telling I4 is the next instruction to be executed. But due to this interrupt, after I3, what is the next instruction that should be executed? IX. But program counter is telling I4. So when IX can be executed? When PC program counter show this I5000 address, then CPU take up IX. So program counter should be repointed to 5000. Okay. Once interrupt instruction is over, completed, then what? From where it should resume this program? From I4. How computer know that I should resume from I4? So whenever an interrupt occur, before servicing the interrupt, the PC value, PC means what? Address of instruction. Which instruction? Next instruction. While I3 is getting executed, next instruction is I4. That address is there with PC. So this PC value preserved. PC value preserved means stored somewhere. Where? On the top of the stack. On the top of the stack, PC value is preserved. So what is that address you preserve on the top of the stack? For word addressable, it is 1014. For byte addressable, it is 1056. Got it? Now, there is one small point here. Suppose I5 is the halt instruction. While halt instruction, if interrupt occur, we all know halt means it's like stop, no further execution. But interrupt occurred while halt. Actually, what is the scenario? First, the current instruction execution is completed, then interrupt is serviced. But current instruction execution means doing nothing. No more operation, no more execution. Think once. So after halt, interrupt should be serviced. It means it is actually contradictory. Because halt says no more execution. But interrupt should be executed. That's why when interrupt occurred during halt, same instruction address is pushed because PC point to this only. PC points to the same instruction because there is no next instruction after this. Got it? So remember this point, it is very important. Okay? Chalo. Now let us start our practice. Consider the program segment below with initial values at 1000, 2000 and 3000 memory locations as 10, 20 and 30 respectively. After the program execution, the value at 3000 memory location would be. Come on guys, solve this and tell me what is your answer. Monica, interrupt will be served. Interrupt will be served. That's why halt instruction execution is delayed. Okay. So what is the answer for this question? Add 1000 comma 2000. What is there at 1000 memory location? At 1000 we have 10. At 2000 20. At 3000 30. 30. Okay. Now add 1000 comma 2000 means at this 1000 address, add the value at 1000 address and add the value at 2000 address and store in 1000 address. That means 10 and 20 are added, that stored back in 10, 1000 address. Similarly, what sub of 3000 comma 2000 means? 3000 value at 3000 minus value at 2000. What is value at 3000? 30. Value at 2020. 30 minus 20, 10 should be stored back in 3000 memory address. Mul I, when you are having the suffix I for the opcode, what that I indicates? Immediate operand. What is called immediate operand? Value is called immediate operand. Means it is telling this 20 is the value, 3000 is in the parenthesis, so it indicates address. So it means at 3000 address, value at 3000 and value 20 should be multiplied and stored back. So value at 2000 is 20, value at 3000 is 10, 20 multiplied by 10, 200 stored here. Okay, Superman. And now div 3000 comma 2000 means at this 3000 memory location, 3000 value should be divided with 2000 memory location value. Means 200 divided by 20, that is 10. Right? So what is the value at 3000 memory location finally? 10. Hence the answer is option A. Clear? Am I clear, everybody? Okay. Next question. Consider the instructions and their respective sizes in words as below. Let the word length is 4 bytes. If all instructions are stored in serial manner, starting from address 5000, then the absolute difference of I3, instruction I3 address while word addressable and byte addressable memory configurations. Read the question properly, try to understand and solve, give your answer. We have 5 instructions I1, I2, I3, I4, I5. Their size in words is 4 words, 8 words, 2 words, 6 words, 2 words. And the size in bytes, one word is given as 4 bytes. So 4 into 4 16, 8 into 4 32, 2 4s are 8, 6 4s are 24, 2 4s are 8. Now word addresses starting from 5000 to 5003, 4 words, so 4 addresses. 5004 to 11, 5012 13, 14 to 19, 20 21. Byte addresses starting from 5000 to 16 bytes means 5015, 5016, 5048, 5056, 5080. So instruction I3 addresses, if you look at, $40, 5048, 5012. So what is the absolute difference? 36. So the answer is 36. Ravi Shankar, we just have 4 topics, brother. In that 4 topics, again you want important? We just have 4 topics. Clear? Question number 3. Assume that a program segment has 4 instructions I1, I2, I3, I4. The size of instruction I is double that of instruction I minus 1, while size of I1 is 1 word. Let word length is 32 bits. The address of I3 with byte addressable memory if program started from 5000 is. Yes, what would be your answer for this question? Everybody keep giving the answers. Yes. Option B, option C. Given there are 4 instructions, I1, I2, I3, I4. Instruction I size is double that of I minus 1, means previous instructions size double. I1 size is 1 word. So I2 size would be 2 words. I3, 4. I4, 8. But given byte addressable memory. So first convert into bytes. 1 word is 4 bytes. So 4 bytes, 8 bytes, 16 bytes, 32 bytes. Starting from 5000, the addresses would be 5000, 5008, sorry, 5000, 5004, 5012, 5020. So instruction I3 address we want 5012. Got it? Question number 4. Let the program has 10 instructions I1 to I10 to execute. The size of first even instruction is 1 word and the size of last odd numbered instruction is 128 words. Each word size is 32 bits. The size of other instructions is twice that of previous even instruction if it is even, half of next odd instruction if it is odd. Then what would be the size of instruction I5? Yes. What would be your answer? We have 10 instructions. First even instruction size is 1 word. Last odd instruction size is 128 words. And the other instructions size is twice that of previous even instruction if it is even. Means I4 size is twice that of previous even instruction I2. I6 size is twice that of I4. I8 size is twice that of I6. And I10 size is twice that of I8. And half of next odd instruction if it is odd. So I1 size is half of I3, I3 size half of I5, I5 size half of I7, I7 size half of I9. That means 64. I5 size 32, half of I7. I3 size half of I5, 16. I1 size half of I3, 8. Now, I want instruction I5 size. I5 means 32 words. But I want in bytes. One word size is 4 bytes. 32 bytes means 32 into 4 bytes. 32 words means. So, 128 bytes. Got it? Next question. Match the following. You are given opcode and the type of instruction. Please match. Ravi Shankar, first understand the question. Every even instruction size is double that of previous even instruction. Means I2 size is 2 into I0. But it is given, it is one word. I4 size is 2 into I2 size. I6 size 2 into I4 size, like that. Similarly, odd instruction size is half of next odd instruction size. Means I1 size is half of I3. I3 size is half of I5 size. I5 size is half of I7 size. In that way, I9 size is given to us as 128 words. In that way, I5 size is 32 words. But one word is given as 4 bytes. So, 32 words means 128 bytes. Okay. Match these, everybody. Branch unconditionally. Program control. Compare. I can match to logical. Complement. Bitwise. Circular right shift. Shift instruction. So, A2, B1, C3, D4. A2, B1, C3, D4. Monica, option D. Okay. Next question. Consider a processor executing the following program segment. R1, R2, R3B general purpose registers. If the program has been loaded starting from the address 2000 in word addressable memory, then the return address pushed on the stack is dash. Consider interrupt occurred during INC instruction execution. यस, फटाफट सॉल्व करो बेटा। Word addressable memory. So if we write addresses, size is directly given in words, so directly you can write the addresses starting from address 2000. So 2000, 2002, 2006, 2010, 18. These are the addresses. Now, interrupt occurred during INC. Then what I said? Program counter points to DEC instruction. Before servicing the interrupt, its address is saved on the stack. So what is the address of DEC? 2010. No, Monica, during INC interrupt occurred. So next instruction address is pushed onto the stack. That means DEC address is pushed onto the stack. The addresses are these: 2000, 2001, 2002 to 2005, 2006 to 2009, 2010 to 17, 18, 19. We know the starting address is what taken always as address of anything. So what is address of decrement? 2010. Got it? So what is the answer? 2010. Now, same given, but interrupt occurred during halt instruction. Then what is the return address pushed onto the stack? Read the question carefully. It is byte addressable memory. What was the address we got in word addresses? Word addresses 2000, 2002, 6, 10, 18. Right? During halt interrupt occurred. What I said? During halt interrupt occurred means halt execution only gets delayed. Means PC will be pointing to the same halt. So the same instruction address is preserved. So 2018 is word address, but byte address I want. So 2018 into 4 you can take 2072 is what preserved on the stack. Sorry, 2018 into 8. That means 2144 will be preserved on the stack. Soham? No. This is for ECE. CSC students, COA marathon already completed. Please find the playlist. In the playlist it would be there. Okay? Everybody, the answer for this is 2144. Fine. Let's proceed to question number 8. Assume that certain processor executing the following instructions. Let size of these instructions is 1, 2, 4 and 6 words respectively. The number of clock cycles for each operation be as follows. Instruction fetch 2 clock cycles, decode 4 clock cycles, memory to register transfer 4 clock cycles per word, register to memory transfer 8 clock cycles per word, arithmetic operation 3 clock cycles. Okay. Now, this is 2 clock cycles per word, instruction fetch also. Instruction fetch also. The total clock cycles required to execute the program would be dash cycles. Means total to execute the program, how much time is required, how many clock cycles are required. Yes. What I said, for instruction execution, mandatory phases are instruction fetch, instruction decode, execution. What is the meaning of instruction fetch? Loading, copying instruction from memory to CPU. So from memory to CPU, how much you can bring? 1 word. But the first instruction size is given as 1 word. Second instruction size is given as 2 words. 4 and 6. So to fetch first instruction, how many clock cycles? 2 clock cycles per word. So it is 1 word, 2 clock cycles. Next instruction, 2 words. Only 1 word we can transfer at a time. So 2 into 2. 4 words. 6 words. Plus. Decode takes 4 clock cycles. Decode is having no effect of size, because whether it is a small instruction or big instruction, control unit decode it in the same way, in the same time, ideally. So we can say it is 4 clock cycles for all instructions. Plus execution means what? Doing that operation, addition, move, store, sub, doing those operations. For addition, addition is arithmetic operation. How much time? 3 clock cycles. Move from where to where? 5000 address to register R3 means memory to register transfer. 4 clock cycles per word it is said, but we don't know how much data we have in the 5000 address. Is it a 1 word data or 2 word data or 3 word data or 6 word data? We don't know. That is not given also. And register size is 1 word. So we are taking ideally the content at 5000 is 1 word. So 4 clock cycles. And store register to memory, that is taking 8 clock cycles. And subtract, again arithmetic operation, 3 clock cycles. Okay. So now it is total 2 plus 4, 6 plus 3, 9, 4 plus 4, 8 plus 4, 12, 8 plus 4, 12 plus 8, 20, 19. Okay. Now 12 plus 9, 21 plus 20, 21 plus 20, 41 plus 19, 60 clock cycles. Okay. Guys, these are the model questions you can expect in the GATE exam. Sure. Next question. Consider the steps for fetching an instruction below. Consider PC is incremented implicitly. Which of the following is the correct sequence for fetching an instruction? Given 7 steps, S1 to S7. In that, which is the correct order for instruction fetch? Instruction fetch means what? Load instruction from memory to which register? CPU's instruction register. Who knows from which address to fetch? PC knows, program counter. So that address is copied into address register. So how this can be copied? Read PC, write MAR. So read PC should be first, write MAR should be next. So S3, S4. So the answer is in these two. Then PC incremented implicitly. PC increments means points to the next instruction. Because this instruction is already copied, so next instruction address PC maintain. It happens implicitly. Means you need not to count the steps for it. Now, at this address, what is there that should be copied? At memory address, which is in the MAR, at that address, what is in the memory, that should be copied into CPU. Where anything gets dumped into CPU? MDR. First, anything comes into CPU to MDR only. So, for this, MAR, read MAR means read the address. Read that address. Read from memory. And where it gets written? In the MDR it is written. So, I can say it is S1. S1 is this only. So, this should be third. This should be fourth. This should be fifth. But what is copied? Instruction is copied. As that is instruction, where it is supposed to be? In the instruction register it is supposed to be, not in the data register. So, copy from data register to instruction register means read from MDR, write into IR. So, read from MDR, this should be 6th, right into IR. This should be 7th. So S3, S4, S1, S5, S2, S7, S6. Option D is the right answer. Ravi Shankar, if this is the very first time, please understand Ravi Shankar, this is Maha marathon which we are conducting for practice purpose. The gate exam is there for you maybe on 5th or 6th. Just 15 days left. So by this time your preparation should already be completed. Now you are starting or learning all these things means it is little difficult. So abbreviations of registers you are unaware means please spend some time, learn CO properly. Then if you practice questions, then it would be more clear, more confident for you. Okay. Next question. A CPU has only 5-byte instruction. A program starting address is 104. Find the correct legal program counter value in between the addresses 201 and 205. Every instruction size is 5 bytes. A program has 5 bytes instructions. Its started address is 104. Ravi Shankar, CO is introduced in this year. Earlier it was not there, only digital circuits, only digital logic were there for ECE students. Okay, CO introduced this time. So we can expect around 4 or 6 questions, or 4 or 6 marks. Yes, Raviteja, correct. So the next instruction size becomes 109, next instruction size 114. That means if you see the displacement between all the instructions, it is 5, 5, 5, 5, 5. So from 201 to 205, which value you get in this 5, 5, 5, if you keep adding, you will get 204. So while I1 is executed, PC points to I2. While I2 is executed, PC points to 114. While the instruction at address 199 is getting executed, while current instruction is this, the next instruction will become instruction at 204. So the PC points to 204. Okay, that is the valid program counter value. Clear? So this is how you can expect questions, and everybody, as it is introduced this time, you need not to expect very complex or very difficult questions. As this is the first time, you can expect some easy to moderate questions from CO, and that level questions only I am presenting here. I am making you practice. Definitely these models will be sufficient. Okay. Shall we proceed to next topic? Sure. The next topic is instruction formats. How you can know this instruction format? Why? Because how to write the instruction? When you write in one way, it means it has some meaning. When you change the order, that may give a different meaning. So, in what format we have to write the instructions? To understand that, first, instruction formats are based on ISA. ISA means instruction set architecture. Based on ISA, the formats are dependent. Okay. So, ISA specify what the processor is capable of and how that can be done. So, based on ISA, we have to derive the format. This ISA can be classified, this instruction set architecture can be classified based on from where the operands are stored, from where you have to fetch. These operands, dear friends, please remember the operands are basically three types. Memory operand, register operand, IO operand or immediate operand. How to know that the operand is a memory operand? You will be given address. When you see address in the operand field, that means it's a memory operand. When you see the register name or register ID, that is a register operand. When you see value directly in the instruction, that is immediate operand. Okay. So, where these operands are stored and how you can name them or refer them, implicit or explicit. Even the upcoming addressing mode topic is also based on this, dear friends. Based on the architecture, formats, addressing modes are defined. So, we have basically three types of organizations or architectures. Accumulator organization, register organization, stack organization. Accumulator organization means all are processed through accumulator. So, accumulator is the implicit or default register here. And general register organization, we have again three types. This general register organization is subclassified into three types. Register organization, register memory organization, memory organization. That means operands are registers. Means add R1, R2, R3. All the operands are registers. So, source is register, destination is register. This register organization is what? Our RISC instruction set architecture follows. So it supports the register operands only. And register memory organization means one operand is register, another operand is memory, like this. One operand is the address, another operand is the register. So one value is fetched from the memory, loaded in the register, passed to ALU, and the task got accomplished. Memory organization means both operands are addresses only. So this is register organization. Stack organization means we will load the operands through push and pop operations. And this stack organization supports immediate operands, means direct values. And what is the register this stack organization use? Stack pointer. This is the special purpose register. So stack pointer is used to implement this stack based instruction, stack organization based instructions. Okay. So this ISA can define different instruction formats. What they are? 4 address instruction format, 3 address format, 2 address, 1 address, 0 address, and RISC format. RISC format supports only register operands. And all the other are CISC instruction formats. CISC means complex instruction set computer. RISC means reduced instruction set computer. However, full forms will never be asked in the GATE exam. Full forms cannot be asked. So, you don't worry about the full forms. So CISC formats, we have 4 address, 3 address, 2 address. So you can specify 3 operand information, 2 operand, 1 operand. So is the number of operands is fixed? No. So CISC supports variable length instruction format. Whereas the RISC supports fixed length instruction format. Okay. And in 3 address, 2 address, 4 address instruction format is outdated. Here 4 addresses or 4 operands we write. OP1, OP2, OP3, OP4. The first operand is treated as destination operand. Next 2 are treated as source operands. And the last operand is treated as address of next instruction. But once program counter register is developed in the CPU, this 4 address instruction format is not in use. The other 3, 2, 1, 0 we can follow. This 3 address, 2 address formats or 1 address formats, the operands can be either memory operands or register operands. Whereas one address instruction format is what? Accumulator based organization. So the implicit register for one address is accumulator. Zero address instruction formats are used by stack organized computers. That means what operands are allowed by zero address? Immediate operands. So remember all these about instruction formats. Now when we are given some space, let's say you are given some 1 kilobyte memory or 12 kilobyte memory, like that, some space is given for you and you have to store all these instructions, means always you give priority for large size instructions. Okay, so high priority we give for large size instructions, means 3 address. First we fill 3 address instructions, then 2 address, then 1 address, like that. Okay, now let us solve some questions on this. See, the question can be like this. If you know the approach, fine. Otherwise, please listen carefully and try to understand the approach. When a question comes like this, how to solve? What is the question? A computer has 32-bit instructions. So instruction size is 32 bits and 12-bit addresses. If there are 252 address instructions, how many one address instructions can be formulated? Given the instruction size is 32 bits. What an instruction will have for sure? Opcode. And I told the priority you should give from large size. So first you should save 2 address instructions. So 2 operands I am taking. What is every operand size? 12 bit. So how many left for the opcode out of 32? 12 plus 12, 24 gone. 8 bits left for the opcode. Right? So with the 8 bits, 2 raised to 8 opcodes possible. 256 opcodes possible. Given there are 242 address instructions. So how many left for one address? 16 opcodes left for one address. So we can have opcode with one operand we have 16 opcodes and this operand can be 12 bit width. So total one address instructions possible are 16 opcodes and this operand can have any address that you can formulate with 12 bit. So 2 power 12 combinations. So this is 16 multiplied by 4096, that is 24576. So total one address instructions possible are 24576. $250. Okay. Okay. 6 only, 6 only. Okay, Monica, Shruti. Chalo. Next, extension to this previous. A system has 16-bit instruction that supports 0 address, 1 address, 2 address instructions. Priyanka Ganeshan, should I ask Rakesh sir or should I not ask Rakesh sir? Okay. Assume each address field is 5 bit. It is designed for supporting 40 number of 2 address instructions. 400 1 address instructions. Then the maximum number of 0 address instructions that can be formulated is. Try doing it. Okay. The instruction size is 16 bits. We give priority always for large size instruction. Means in 0 address, 1 address, 2 address, 2 address is what? Large size. Given every address field size is 5 bit. So 5 bit for OP1, 5 bit for OP2. Left are 6 bit for the opcode. With 6 bit, total 2 power 6, 64 opcodes possible. In this 64, 40 are there 2 address instructions. So left are 24 for 1 address and 0 address. So total 1 address possibilities are 24 into 2 power 5. Just previously we have solved, no, like that. So it is 24 into 32. This is 24 2s are 48. 24 3 is 72 plus 4, 76 maybe. Yes. Yep. Rajshri Joshi, it is mentioned under digital circuits. Rajshri Joshi, under digital circuits, you see, at last you will have this computer organization title with 4 topics. You will get 4 to 6 marks from these topics. So to skip or not, that is your call. I don't say. Okay. But it is in the syllabus. Now, in this 768 given, there are only 400 one address instructions. That means 368 are left for 0 address. Right? So total 0 address possibilities. 0 address means what? Value. Memory operands are not there, but values are there. So we have 368 0 address. Value not given, but we know address field size is 5 bit. So any value should be of this range only, within this range only. So 2 power 5, 5 bit, with 5 bit how many values are possible? 32 values, 5 zeros to 5 ones. So that is equal to, let me use the calculator, 368 into 32. So 11,776 total 0 address possibilities. So that should be your answer. Okay. Thank you, Rajshri. Thank you. Clear? Next question. Choose the correct statement or statements from below. MSQ question can be like this in a simple way. CISC supports only register operands. CISC supports fixed length format. RISC supports variable length format. RISC supports only register operands. Which is correct? CISC supports only register operands. No, it supports memory operands, IO operands also. CISC supports fixed length format. No. RISC supports variable length format. Wrong. RISC supports only register operands. Correct. MSQ doesn't mean always multiple should be correct. Even one also can be correct. That is what the tricky part in MSQ type. Even one can be correct. But you should select all correct options, then only you will be awarded mark. I think you know it. Okay. Question number 14. Match the following. And it is the previous ESE question, dear friends. In engineering services, this question was asked. So similar question you can expect in the GATE. And in the GATE CSE, several times this type of questions were asked. So we can expect this model. What is your answer? Add R1, R2, R3. 3 operands are there. 3 are registers. In the fourth also 3 operands are there. 3 are addresses. So how we can distinguish now? Only register operands means RISC format supports it. This we can relate to 3 address and 2 addresses, 1 address. So 1D, 2B, 3C, 4A, option B. Okay. Yep. Next question. A processor has 8080 distinct instructions and 50 general purpose registers. A 32-bit instruction word has opcode, 2 register operands and an immediate operand. The number of bits available for the immediate operand field is yes. What is your answer? Okay. Given 32-bit instruction, instruction has opcode, 2 register operands, 1 immediate operand. What is immediate operand means? Value. Now, how many bit we use to represent the register? It is given there are 50 general purpose registers. 50 GPRs are there. So, log 50 base 2 seal value. These number of bits for each register. So, that is 6 bits. Given there are 80 distinct instructions. So, the distinction can be in the opcode. So, 80 distinct instructions indicates 80 distinct opcodes. So, 80 opcodes means for a opcode log 80 base 2 seal value bits for each opcode. So, that is 7 bits for the opcode. And how many left for the immediate operand? 6 plus 6, 12 plus 7, 19. 13 bits left for the immediate operand. So, that is what the answer, 13. Clear? Next, look at this question. A processor with 32 registers and instruction set of size 12. Every instruction is having 5 fields: opcode, 2 source register identifiers, 1 destination register identifier, and 14-bit immediate value. Each instruction must be stored in byte aligned fashion. So, byte alignment means a byte is given completely or none. So, a byte completely should be on one name or none. That is what byte aligned. If a program has 200 instructions, the amount of memory wasted by the program text is. Given every instruction has 5 fields. What are they? Opcode, 2 source register identifiers, 1 destination register identifier, and a 14-bit immediate operand. So, that length is 14-bit. Given there are 32 registers. So, 5-bit per register. Now, instruction set has how many? 12 instructions. So, definitely set will have 12 distinct instructions. So, 12 opcodes. So, 4-bit for the opcode, log 12 base 2. So, what is the total length? 4 plus 15, 19 plus 14, 33 bits. 33 only? Means How many bytes required or allocated for every instruction? 4 bytes not sufficient. So 5 bytes allotted or allocated for each because it is byte aligned. That means 40 bits allocated. So for total program 200 into 40 bits allotted. But in this only 33 bits are what instruction required. Wastage. So wastage is in every instruction 7 bits are getting wasted. So 1400 bits is the wastage. That means 1400 by 8 bytes. That is 175 bytes is the wastage. So we want the wastage in bytes, hence you have to write 175. Got it? Everyone, did you understand? Please respond. Yeah. Thank you, Rajshri. Fine. Okay. So from instruction formats, dear friends, this is how we can expect the questions. Now let us move to next topic, that is addressing modes. Okay. So what is an addressing mode? How we specify the operand information, that is called addressing mode. The operands of the instructions can be located either in memory operand, or register operand, or value, that can be immediate operand. If the operand is placed in the memory, then instruction provides the location address in the operand field, right? And there are many methods to specify the address. Every method for specifying that operand address in the instruction is called addressing mode. Basically, these addressing modes are 3 types. The basic classification is basically 3 types, you can say. Memory direct, 2 types. Okay, in this way 3 types you can say: direct, indirect, actually. Okay, in the direct you can have 3 types of direct addressing modes. memory direct, register direct, value direct. Value direct is what? Immediate mode. So basically you can divide addressing modes into two types: direct, indirect. Direct into three types, indirect into several categories. So altogether in this CO limitation, computer organization limitation, I can say addressing modes, different addressing modes we have are this: direct, indirect, register direct, register indirect, auto increment, auto decrement, indexed, relative, based, implied, immediate. So direct addressing mode means the given address is having the operand. So given address has the operand. Indirect means the given address has another address. That address can have another address. That can have another address. Somewhere you get the operand. Register direct means the register in the instruction has operand. Register indirect means the register got address, that address has operand. Auto increment, auto decrement means the given address is, let's say, A1, A2 is the actual address. So effective address or actual address is, effective address is next address to the given, or effective address is previous address to the given. Indexed means to the given address, index register value you add, you will get the actual address. To the given address, program counter value you add, you will get the actual address, that is relative. To the given address, base register value you add, that is the based mode. Implied mode, the address is implicit. Immediate mode means instruction has values directly. So there are different ways to specify the operand information. These are different ways. Along with this, you may have even some more additional addressing modes, but in the CO limitation we can discuss this. Okay, so please do revise about these addressing modes, everybody. These are very important. Okay. Now let us solve some questions. From these addressing modes. Okay. Chalo. In the register indirect addressing mode, options: operand is inside the instruction, address of operand is inside the instruction, register containing operand is in the instruction, register containing address of operand is inside the instruction. So when you call it as register indirect addressing mode, Monica, nahi beta. The operand is in the instruction, that is immediate. Address of operand is in the instruction, that is memory direct. Register containing operand, that is register direct. Register contain address of operand, that is register indirect. So we want register indirect, hence option D, Monica. Okay. Next, match the following: absolute addressing, scaled addressing, auto increment addressing. On the other side, you have some description. Yep, option C. Okay. Absolute addressing means memory direct addressing mode is also called as absolute addressing mode. So it is operand is effective address. Scaled addressing mode is the other name for indexed addressing mode. So operand is at an offset to the given address. Auto increment, operand is the next address. So 1B, 2A, 3C. Yes, Monica, you are correct. Very good. Okay, next question. How is the effective address is calculated in scaled addressing mode? Let destination operand be R1, source operand be A1. So how do you get the effective address in the scaled addressing mode? What is the other name for scaled? Indexed. If you know this term, you will get the answer easily. If you don't know that indexed mode is also called as a scaled mode, then you may give wrong answer. So to the given address, index register value is added. Then you will get indexed, then you will get effective address. Okay? Yes, right. Next, the number of memory accesses required for each operand in memory indirect addressing mode is. In memory indirect addressing mode, how many memory accesses required for each operand? Exactly 1, exactly 2, at least 2, at most 2. Indirect means you are given some address 1000, 2000, something like this. So 2000 is having address 3000. 3000 may have address 4000. 4000 may have address 5000. 5000 is having the value, or even it can be extended. So minimum 2 memory references needed, and it can be even more than that. Exactly one is memory direct. Memory direct. Okay. Sure. Memory direct, even register direct also exactly one. Register indirect also exactly one. Sure. Next question. Consider the addressing modes and their applications given below. Which of the following pairs are valid? Relative addressing vector implementation, scaled addressing vector implementation, based addressing program relocation, based addressing program sequencing. It is MSQ question. Vector means one dimensional array. For array implementation, indexed mode. So array implementation, indexed mode is used. For program relocation, based mode. For program sequencing means what is next, what is next. That sequencing के लिए program counter use करते, मतलब relative addressing. So relative addressing for vector implementation, no. Scaled for vector, correct. Based for program relocation, correct. Based for program sequencing, no. So B and C are the valid pairs. Okay. Next. Total number of memory accesses required to complete the following instructions execution is: add R1, R2, R3. You see the instructions. Suppose every instruction is one word, as well as every address, means every data is one word. We know memory reference needed when you fetch. So instruction fetch, operand fetch. So first, for this instruction fetch, one memory reference. And what are the operands? Register operands. So no need to fetch the operands from memory here. Second instruction, for instruction fetch one time. For operand fetch, this is register indirect, means that register has address, at that address value is there, so one time. Here instruction fetch 1, for operand fetch 2 times, because you see there are 2 parentheses, means register has address, at that address another address, at that address value. So total is 6 memory references. Okay. So in this way, from addressing modes, you can expect the question. Before we proceed to next topic, dear friends, GATE and ESE test series is now available for you to strengthen your preparation. In this test series, you will get 4000 plus practice questions with 40 plus full length mock and 30 plus subject wise mock with virtual calculator, detailed mock analysis. So completely whatever needed for your preparation, all will be provided with this test series. So visit our BEP app or website and avail this test series and prepare well. Okay. Now you can download our GATE preparation free ebook. You will get the details, notifications about our scholarship tests and also our free GATE workshops if you subscribe to our BEP channel and press the bell icon. So do subscribe and enable your notifications and register for these with the descriptions, with the links in the description box. Okay. Now let's move on to the next topic, instruction pipelining. Okay. So I'll speed up the things, guys. We know when there are multiple instructions, we can execute them in three ways: serial processing, parallel processing, pipelined processing. Serial means after completing one instruction, then another, then another. Suppose when you take any instruction, I said there are three phases mandatorily, right? But there could be some other optional phases. So instruction execution involves instruction fetch, instruction decode, operand fetch, execution, memory or write back, interrupt. Like this, there are multiple phases. In this operand fetch, these are optional. Okay. So suppose an instruction has three steps to execute. So serial processing means first instruction, all the steps are over. Then second instruction, all the steps should be done. Then next instruction, all the steps. Like this, one after another, when we complete one by one, that is serial processing. Parallel processing, all instructions first step together, all instructions second step together, third step together, like this. Pipelined processing means no similar stage overlap. So like this, if you execute, that is pipelined processing. I'm just revising it, okay? So let n be number of instructions, k be number of stages, and t be the stage time, then total time to complete n instructions in serial processing is n into k into t. This serial processing is also called as non-pipelined processing. Similarly, in the parallel processing, how you can calculate the total time? K into T. And in the pipelined processing, how we can calculate? N minus 1 plus K into T. So these formulas are very important. Now, parallel processing is just a theoretical possibility, practically not possible. So we have pipelining technique and serial processing technique. In these two, how we calculate the speed up? That is amount of growth in performance of computer by switching from non-pipelined mode to pipeline mode. So, non-pipelined time by pipelined time, that is nkt by n minus 1 plus k into t. So, tt gets cancelled. So, speed up you can write as nk by n plus k minus 1. And efficiency, speed up by number of stages. So, nk divided by n minus n plus k minus 1 by number of stages k, that is n by n plus k minus 1. Sir, why you are writing number of stages, sir? Because the ideal speed up or maximum speed up, that is k, guys. Ideal speed up or maximum speed up is with the order of number of stages. So, efficiency is S by S max, achieved speed up versus with respect to maximum speed up. So, that is how we write K. Or in the phase time diagram, how many boxes you utilize in the total boxes, that is efficiency. Hi Akash Gautam, good afternoon. Okay. And throughput, how you can define throughput? How many instructions you are executing with respect to total time. So, look at this question. Suppose an unpipelined processor with a 25 nanosecond cycle time is divided into 5 pipeline stages with latencies. If the pipeline latches latencies are 1, 2, 1, 3 and 1, what is the cycle time? How we calculate small t p? This is cycle time in pipelined processor. That is maximum of stage delays plus interstage delay. TD is what? Stage delay. TI is interstage delay. So, that is maximum of 5 plus 1, 7 plus 2, 3 plus 1, 6 plus 3, 4 plus 1. That is maximum of 6, 9, 4, 9, 5. So, this is 9 nanoseconds. Okay. Next, in an unpipelined machine, assume that times required for 5 functional units which operate in each of the 5 cycles are as follows. Addition of buffers add 1 nanosecond overhead. Find the speed up versus unpipelined execution. Speed up is non-pipelined time by pipelined time. What is non-pipelined time? Sum of all the delays. Pipelined time, just now I said max of TD plus TI. Guys, all these formulas you have to remember. This will help you in solving the problem. So, non-pipelined time is 10 plus 8 plus 10 plus 10 plus 7. That is 45. Pipelined time is max of 10, 8 Okay, 10 plus 1, 11, 8 plus 1, 9, 10 plus 1, 11, 10 plus 1, 11, 7 plus 1, 8. So that is 11 nanoseconds. So speed up is 45 by 11, 4.1 approximately. Okay. Yeah. Next question. A non-pipeline system takes 50 nanoseconds to process a task. Same task can be processed in a 6-segment pipeline with a clock of 10 nanoseconds. Determine the speed up ratio of the pipeline for 100 tasks and what is the maximum speed up. In the previous engineering services paper, this question was asked. What is the maximum speed up? I said K. K is number of stages, that is 6. And how do you find the speed up? Non-pipelined time by pipelined time. What is non-pipelined time? N into K into T. N is 100. And for one task, it is taking 50 nanoseconds. So this is 5000 nanoseconds. And pipeline time, N minus 1 plus K whole into T. One thousand minus 1 plus 6 into T is 10 nanoseconds. This is 1000 minus 1. 1005 into 10, 1050 nanoseconds. So speed up is 5000 by 1050. You will get 4.76. So 4.76 and max is 6. Clear? All right. Next. The stage delays in 4-stage pipeline are 800, 500, 400, 300 picoseconds. The first stage, that is 800 picosecond delay wala, is replaced with functionally equivalent design involving 2 stages with respective delays 600 and 350 picoseconds. The throughput increase of the pipeline is -%. What is T max of TD plus TI? It is not given. TI is not given. So max of 800, 500, 400, 300, that is 800 picoseconds. Now 800 picosecond stage is replaced by 2 stages. So let that be T1. Now when it is replaced, now what would be the max of this 600. So what is the throughput increase? 800 minus 600 by 600. 200 by 600. 1 by 3. 33.33%. So that is the throughput increase. Okay, everybody. Next, look at this model question. This is very popular model question, dear friends. This type of question you can expect in the GATE exam. Definitely, of course, all are GATE expected questions only. This is more probable. You are given some instructions and every instruction has phases IF, ID, OF, PO, WO. Okay, don't mind much about those meanings. Okay, for you guys in the CSC that is different case, but for you, you can just expect some basic level or moderate level questions. Given these phases take 1 clock cycle for any instruction, but PO takes 1 cycle for add, 3 cycles for mul, 6 for div. Operand forwarding is used. Please remember, operand forwarding means it is the solution to handle data hazards. That to read after write hazard. So, no need to worry about the dependency. That is the meaning. What is the number of clock cycles needed to execute the following sequence? So, how to solve this model question? We are given mul, div, add, sub, right? And we are given 5 stages: instruction fetch, instruction decode, operand fetch, perform operation and write operand. Instruction fetch, decode, operand fetch, write operand takes 1 clock cycle each for any instruction. But PO takes 3 cycles for mul, 6 cycles for div and 1 for add and sub. Now what we have to do is, you have to draw the space-time chart. Phase time diagram or space-time chart. What is that, sir? See, you should make sure no two similar stages overlap at any given cycle. So first instruction, IF take 1 cycle, ID 1, OF 1, PO 3 cycles, write operand 1 cycle. Okay. Now, first instruction you should execute in pipeline with the other, I1 with I0. What is the rule? No two similar stages should overlap. So, here IF 1 cycle, ID 1 cycle, OF 1 cycle, PO I can't do because another PO happening here. So, until that PO is over, I have to wait. This is called stall cycle. Now I can do PO, it takes 6 cycles. Then WO 1 cycle. I hope now you understood the trick. So I2 in pipeline with other, make sure no two similar stages overlap. So IF here, ID, OF. I can't do PO until the other PO is over. So here PO and then WO. I3 here, IF, ID, OF, PO, W. So total how many clock cycles? Count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So total clock cycles needed are 50. Got it? So this is how you can expect questions from instruction pipelining topic. Now let's move on to ALU data path and CU design. This question, this topic, let us directly practice the questions. Through questions you can revise the concept. Okay. Here is the first question. Consider a CPU with 5 different types of control signals to generate multiple types. We have 5 types and every type has how many given. The total number of bits required in vertical and horizontal microprogramming. In horizontal microprogramming, if we are having n control signals, we require n bits. But in vertical microprogramming, if you have n control signals, they are n coded. So log n base to seal value number of bits required. Okay. So in horizontal type 1, here let me write 20 signals are there, so 20 bits, 10 signals, 10 bits, type 3, 15 bits. How many signals are there? Those many bits, because every signal require 1 bit. Type 4, 60 bits, type 5, 30 bits. So what is the total? 135. And in vertical microprogramming, if there are n signals, log n base 2 bits required. So we have type 1 20, so log 20 seal values we have to take, that is 5 bits. Type 2 log 10 4 bits. Type 3 log 15 4 bits. Type 4 log 60 6 bits. Type 5 log 30. Of course, seal value, please understand, that is 5 bits. So what is the total? Total in vertical, five plus 4 plus 4 plus 6 plus 5, 24. So vertical and horizontal, in that order I want. So 24, 135. Okay. Next, a hardwired CPU uses 10 control signals S1 to S10 in various timestamps T1 to T5 to implement 4 instructions. Which of the following expression represent circuit for generating control signal S8? What we do? Identify where you have S8 first. identify where you have S8. Let me change the color. I have here S8, here, where else? That's it. Okay. So now during time T2 for instruction I2. So S8 is equal to I2 into T2 plus I3 into T2 plus I1 into T5. So I1 T5 plus I2 T2 plus I3 T2. So option C is the right answer. Okay? It's very simple. Next, look at this. Consider an instruction. The following steps are used to execute it over the given data path, blah, blah, blah. Which of the above is the correct order of execution? PC incremented appropriately. If you observe, these are again the steps for instruction fetch. So first, from program counter to address register, we will copy. This explanation I have already given in other question. So this should be first. Then you will read from the memory, that will be in the data register. From there, you will write to instruction register. So this is second. Now if you observe this given data path, first operand is through temp1. Look at that diagram, guys. Temp1. Second operand directly we are supplying. So first operand from temp1. Second operand you supply directly and add. Then write the value in the temp2. You see the out arrow from ALU is to temp2. So that is last. So you can say 4, 1, 3, 5, 2. 4, 1, 3, 5, 2 option B. Okay. In this way, we can solve. Next. A CPU has only 3 instructions, I1, I2 and I3, which use the following signals. Which of the following logic functions will generate hardwired control for the signal A in? A in. So identify where you have A in. Here, here, here. Now write SOP form, sum of products form for A in. So A in is equal to, if you observe one commonality, during time T3 for all the instructions it is occurring. So during time T3 for all the instructions, I1, I2, I3 plus during time T1 for I1 plus during time t2 for I3, also during time t4 for I3. When it is for all the instructions, you can write just t3 plus during time t1, t4 for I1 plus t2 into I3 plus t4 into I3. So this is the control signal for A in. That is option A. Okay. Next, consider the following common data path. The instruction add R0, R1, R2 has register transfer interpretation, blah blah blah. The minimum number of clock cycles needed for execution cycle of this instruction is. How many clock cycles needed minimum? Observe the data path. Observe the data path. Through S first operand, through T second operand we are supplying, but actually operands are in R1 and R2. So in the first clock cycle, R1 out, S in. In the next clock cycle, S out, ALU in. In the next clock cycle, wait. R2 out, T in. Okay. Then S out, T out, ALU is taking it, add. In the next clock cycle, ALU out and R0 in. Then result is coming in R0. So how many clock cycles total? 1, 2, 3 and 4. So total 4 clock cycles. Minimum. Okay. That's all about the 4 topics of computer organization and architecture. We are coming up with Master MSQ series from today. So join these MSQ classes without fail. These are for you. And this is my Telegram group link. If you have not joined yet, you may join to connect with me for doubts, PDFs and for any other guidance. Okay, thank you so much for joining the session. Keep liking the session, keep sharing it, and do subscribe to our BYJU'S exam prep channel. I hope this marathon helped you in revising the 4 topics of computer organization syllabus which is added recently for ECE students. Is it helpful? Everybody, was it helpful? Keep learning, keep growing. I wish you all the very best. Thank you guys. Thank you so much for joining the session. See you in the next session. Till then, have a great time. All the very best again. Thank you. Take care. Bye-bye. Monica, please check the YouTube channel once. There already some classes are scheduled so that you can find the time. Okay. Currently, I am not aware of it. That's why. Thank you. See you guys. Take care. Bye-bye.